Today, we're going to talk about even more substitution because it's such a useful process. It takes a complicated problem, turns it into a simpler problem that we can solve. Our integral in x is a mess. Our integral in w is nice and simple, so that's the problem that we want to solve. We just change what the problem is. The most important question in substitution is, what's my dw going to be? If I want to make the substitution w equals g of x, what else do I need to make that substitution work? That's a mouthful, so I just say, what's my dw? You make your choice for w, and then you figure out what the dw has to be, or what you need for the dw to make substitution work. All right. Let's take a look at the category of problem that we want to look at today. And it's going to seem like a strange category, but it's a great substitution exercise. And it's going to be products of powers of trig functions. Today, we want to look at products of powers of trig functions. Specifically, combinations of sines and cosines, combinations of secants and tangents. We can remember, think back to our derivatives. Derivative of sine is cosine, derivative of cosine is negative sine. Those two are related. So if w is equal to sine, I need one factor of cosine to be the dw. If w is equal to tangent, I need secant squared to be the dw. If w is equal to secant, I need a secant and a tangent to be the dw. That's the game in substitution. Whatever substitution you want to make, what's your dw going to be? Because all those x's have to go. So specifically, in the category of products of powers of trig functions, I want to talk about integral of, let's say, sine to the m x cosine to the n x to the x, and pairs of secants and tangents. Secant to the m x, tangent to the n times x to n. The bigger question that eventually we're going to arrive at are, what integrals of this form are not substitution? That's really the question that we're going for. What integrals of this type are not substitution? At this point in your calculus career, I have not told you why we care about products of powers of trig functions. I'm framing it as an exercise in substitution so that we can think about, what's my dw going to be? But more importantly, I care about what products of powers of trig functions of these forms, sines and cosines, secants and tangents, cannot be done with substitution. This is a fun exercise. That's right, fun. Fun, damn it. So what we want to do is think about how substitution works. If I make this substitution, w the g of x, what do I need to be the dw? What other tools do I have, especially if I've got combinations of sines and cosines and secants and tangents? Then once we get through that, you can wonder why I don't have cosecant and cotangent, because those are connected through derivatives as well. It turns out, for the long-term goal of what we're trying to do here, we don't need cosecant cotangent. Secant tangent is what we're going to be using. In some alternate universe, I said just exactly the opposite of that. So, well, you'll be wondering why I didn't include secant tangent. All we need is cosecant cotangent. But in this universe, secants and tangents are what we use. I think in some of those other universes, they're like left is positive and up is positive. You know what I mean? It's all we're like, oh, no, look, right is positive. But those dudes read like down to up on the page. It's really weird. Been to all these other universes to see what things are like. Sometimes we make strange choices. But the point is, they're kind of completely arbitrary choices. All right. Let's talk about these products of powers of trig functions from a substitution standpoint. And the question is, if I want to make a particular substitution, what do I need to have to be the dw? What do I need to make that substitution work? So if I want to say w is equal to sine of x, what do I need to be the dw? Derivative of sine x is cosine x dx. The important thing to note here is that I need one factor of cosine to be the dw. I need one factor of cosine to be the dw. The important thing to recognize here, if we want to substitute sine x, if we want w is equal to sine x, then we need one factor of cosine x. We don't just need cosine, we specifically need one factor of cosine. The reason I'm going to specify that there's one factor of cosine is that only one factor of cosine gets to be the dw. You can think of it that way as well. So if I've got 5 factors of cosine, I need one of them to be the dw, and we're going to have to figure out what to do with the other 4. Here's why it matters, why the count matters. It's not just we need a cosine. On the other column, one of the substitutions we might make is tangent. If w is equal to tangent x, if I want to make this substitution, then dw is secant squared. So if we want w equals tangent x, then we need 2 factors of secant. So if my integral has some tangents in it and only one factor of secant, we cannot make the w equal tangent x substitution. Because to make the substitution w is equal to tangent x, I need 2 factors of secant to be the dw. Similarly, oh, go ahead.
So for this secant squared, we need 2 factors because it's squared.
Because it's squared. So if you want to say w is equal to tangent x, then you need 2 factors of secant. If I have secant to the first and tangent to the fourth, we can't do the tangent substitution because we only have one factor of secant. Fortunately for our heroes, there is another. Just like friggin' Skywalker. It's like the only family in the whole galaxy. If we want to make the substitution secant x, then we need one factor of secant and one factor of tangent to be the dw. I need one of each. then dw. So derivative of secant is secant tangent. In the previous one that I was thinking of, if I have one factor of secant and 4 factors of tangent, I can't make the tangent substitution because I need 2 factors of secant for that substitution. But if I have 1 factor of secant and 4 factors of tangent, I can make the secant substitution, even though there's only 1 factor that's going to contribute to the dw. So I have 1 factor of secant and 1 factor of tangent to be the dw, and then 3 factors of tangent left over. That still doesn't work, but the idea is what's going to be my dw. Similarly, on the cosine side, if we want to make the substitution w is equal to cosine x, then dw is minus sine x to x. How's everybody okay? Here's the other tool that we want to remember from our toolbox. Sine and cosine are related with the Pythagorean identity. Sine squared plus cosine squared is equal to what? Sine squared x plus cosine squared x is equal to 1. So that's the other thing, the other tool that we have in the toolbox. Have you read? The other tool is that sine squared x plus cosine squared x is equal to 1. And I can use this identity to replace cosines and sines, or with cosines with sines, and sines with cosines, but only if they come in pairs. Cosine squared is equal to 1 minus sine squared. And sine squared x is 1 minus cosine squared x. Also notice that secants and tangents are related with their own Pythagorean identity. And we can get, if we forget what that relationship is, we can just take the one that we are not allowed to forget. If you forget the Pythagorean identity for sines and cosines, you need to knock that off and start remembering it forever. Because that's how math works. There are certain things that you just have to know all the time. It seems like a lot to remember because it's a lot to remember. You have to remember all of it all the time in perfect detail. That's not asking too much, is it? So let's suppose that we forget how secant and tangent are related through their Pythagorean identity. We do know that sine squared plus cosine squared is equal to 1. And if we divide this through by cosine squared, we'll have sine squared over cosine squared is tangent squared. Cosine squared divided by cosine squared is 1. And 1 divided by cosine squared is secant squared. And then we can just start turning this around. Secant squared is 1 plus tangent squared. And I could solve this for tangent and say that tangent squared is secant squared minus 1. You can either remember this as 4 separate things or for variations on one thing. So what we notice is that sine and cosine are related, but through the Pythagorean identity, but they're related in pairs. I can replace two factors of cosine with 1 minus sine squared. Over on the other side, secants and tangents are related in pairs. I can replace two factors of secant with tangent squared plus 1. So tangents and secants are related in pairs. Sines and cosines are related in pairs. All right. Let's take a look at an example. Let's suppose that we wanted to integrate I think I want sine, yeah, sine, go with sine to the fourth x cosine x dx. This is nice and straightforward. It might not be obvious to you at this point because it's so early in your integration career. But when I look at this one, there is an obvious substitution to make. What substitution would you make? What does it look like? We got sine to the fourth times cosine x. It's like set up for you. What did I do? Put this cosine x there to be. I set this up so that's your dw. The cosine x is going to be your dw. It's even sitting there right next to the dx. They're called pick me, I'm the dw. And that tells me if cosine is going to be the dw, w is going to be sine. That substitution will work. So if w is sine x, then dw is cosine x dx. And my integral, oh, and then we have to identify what the outside function is. And that's this 4 over here. Our outside function is sine the fourth power. So that's the thing that we're going to be integrating. So our integral, when it comes down to the integration part, we've got a 1/5 be a 1/5 w to the fifth. Because of the choice that we made right here, where w is equal to sine x. We know that this substitution will work because I have one factor of cosine x to be the dw. And that tells me that my function that I'm integrating is just w to the fourth. And so that's what our substituted integral looks like. Sine to the fourth, sine is w. It's being raised to the fourth power. And the cosine x dx is dw. This is a substitution that's working out. So now we integrate. The integral of w to the fourth is 1/5 w to the fifth. I spelled 5 wrong. How many w's are there in 5? Half, because it's FIVE, and a v is a half of a w. We call it w, it's a double v. But anyway. 1/5 w to the fifth power plus c. I don't have the integral in dw because we've integrated. And now I just need to replace the w with what it represents, which is sine x. So we're going to have 1/5. W is sine of x. And sine is being raised to the fifth power. questions? Is everybody okay? Everybody's, of course, we're all okay, because I did this problem on the first day of substitution, it was a 3 instead of a 4. Everybody remember, this is nice and straightforward. Now we're going to look at a variation. Any questions? Not enough space. If the 4 is a variable, then we're making much more complicated functions. Because right now, all we get to do is take a variable x, raise it to a constant, or we can take a constant and raise it to the x. We don't want to take a variable x and raise it to the x. And we certainly don't want to stick sine of x and raise that to the x power. I mean, we can, but we're not there yet. So that's for future. Good question, though. What if there are variables everywhere? Right now, we get to just do those two. Variable raised to constant or constant raised to variable. I'm going to make a small change. I'm still going to have a sign to the 4. But now I'm going to have a cosine to the 3rd x to x. In this case, we're going to make the same substitution. We're going to try w equals sine x. If w is equal to sine x, then dw is cosine x. And I have one factor of cosine x. I also have 2 factors of cosine x left over that I'm going to have to deal with. But just on the previous page, we talked about Pythagorean theorems, so you can probably guess what I'm going to do with those 2 factors of cosine. So if I make the substitution, w equals sine x, then dw is cosine x dx. What will make the substitution work is 1 factor of cosine. We have that because we have 3 factors of cosine. One of them will be the dw, and I have to do something else with the other 2. So we have 3 factors of cosine. One of them will be the dw. So the way I'm looking at this, I have a sine to the 4th. One of the factors of cosine is going to be the dw. Then there's 2 factors of cosine that are left over. So here's what we're looking at. Sine is what I'm substituting. So that's going to be a sine of x to the 4th power. One factor of cosine is going to be the dw, but they'll have 2 factors of cosine left over. Cosine squared x. So at the end there's that cosine x dx, that's going to be my dw, but I've still got this cosine squared. Fortunately, there's 2 of them left. So we can just grab our Pythagorean identity and replace cosine squared with 1 minus sine squared. The reason that this is useful is that now instead of cosine squared, I've got 1 minus sine squared, and sine is W. So this is just 1 minus W squared. And then this single factor of cosine is going to contribute to the dw. So my substituted integral has a W to the 4th power times 1 minus W squared. And then that one factor of cosine is dw. This is a substitution that worked. It worked because we had 3 factors of cosine. One factor to be the dw, the other 2 we were able to replace with the Pythagorean identity. Any questions? Now I can write this as powers of W, so we should. And I'm just going to drop to monochrome. We distribute W to the 4th minus W to the 6th, dw. We integrate 1/5 W to the 5th minus 1/7 W to the 7th plus C because we've integrated. And so our final answer is a 1/5 sine to the 5th x minus 1/7 sine to the 7th x plus C. How's everybody okay? So have 3 factors of cosine. One will be the dw. The other 2 get replaced with the Pythagorean identity. How's everybody okay? Let's suppose that I did not prime you to say W is equal to sine X before with the previous problem. You didn't really have a choice other than to make W equal sine X your substitution. The previous one was W equal sine X. I just changed cosine to cosine cubed, and I put sine first. So if with no direction, you'd probably say, I don't know, maybe sine, and you'd have been right. What if you try to be different? What if you say, well, I don't want to make sine X. I want to do cosine X. You can do sine X like all those Brittany and Justin wannabes. But I'm going to be different. And I'm going to make cosine X because it's more negative. And I can be more goth to have more negatives in things. What if we tried to make the substitution W is equal to cosine X? Would that work here? It kind of sounds like no, the way I'm setting it up. That was really leading. The defense is like, going, objection. Prosecution is clearly leading the class. And then I'd be like, oh, dude, that's what I'm supposed to do. I'm supposed to ask leading questions. You know. So take a minute and think about what happens if we make W equal cosine X. Don't worry about the negative that shows up. That's a constant. That's not the problem. Take a moment and think about what's the problem going to be? What if we tried the other substitution? What if we tried w equals cosine x? If w is equal to cosine x, what do we need for our dw? If w is equal to cosine x, then dw is minus sine x. The negative isn't the problem. We just need one factor of sine to be the dw. What's the problem in this integral with needing one factor of sine to be the dw? If one of those four factors is the dw, how many are left over? 3. What's the problem there? We'll have one left over. 2 of them can be replaced with 1 minus cosine squared, but then I have another one. I don't have an even power of sine or sine that we can easily convert to cosine. So it's going to be a minus dw is sine x to x. But in the substituted integral, I'd have one factor of sine, oops, I have minus one factor of sine. I don't need that yet. I'm not doing this yet. If one factor of sine is going to be my minus dw, I have 3 factors left over. To make the substitution w equal cosine x, I need one factor of sine to be the dw. So sine x is going to team up with the dx over here on the end. That will form a minus dw. So what's left over is an odd power of sines. And we won't be able to convert to cosine x without introducing radicals. Sine squared is 1 minus cosine squared. But then there's one factor of sine left over. It would have to be a square root of 1 minus cosine squared. No, thank you. That makes things worse. We'd end up with a radical, which is not normally a problem, but inside that radical will be 2 terms. It would end up looking like the square root of 1 minus cosine squared all to the 3rd power. No, no, yeah, no. We don't want to introduce radicals, especially if those radicals are going to have more than one term in them. That just makes it worse. Now you might not believe me. You're like, oh, dude, this should work out just fine. And to that I would say, okay, do that then. And then come back to me tomorrow and see if we want to try something else. This is especially true since we could just have done what we did in the previous one. So this tells us when we have products of powers of sines and cosines, how we are going to make our substitution. Let's look at another one. This is a fun one. I always do this one. our substitution is obviously going to be cosine, right? It's the only thing that we have available. We have to make the substitution cosine, right? You can tell by the tone of my voice that the answer is no. What if we tried to make cosine? If W is equal to cosine X, then dW is minus sine X. Do we have any factors of sine? Sort of. Because I could take these cosines and I can convert some of them to sines. But what are the exponents on those sines going to be? 2. And that's a problem. So here's why this problem is so cool. We're not going to make the substitution cosine, even though it's like, oh, the only thing you can substitute is cosine, right? No, we're still going to make the substitution sine. Why are we going to make the substitution sine instead of the substitution cosine? What is it about? Why is W equal cosine X dx, or cosine X not going to work, where W equals sine X going to work? If we make a substitution W equals sine X, what is going to be our dW? dW is cosine X dx. One of the cosines will be the dW, and how many are left over? Start off with 5, one's going to be the dW, 4 are left over. An even power of cosines we can convert into sine. Odd powers of sines and cosines can't easily be translated into the other one. So the problem here is not that when we do dW, it's minus sine X dx. It's not that we look at this and say there aren't any sines running around. That's not the reason that this substitution is not going to work. It's not about the no sines being around, because we know we can trade our sines for cosines and our cosines for sines, but only so long as they come in pairs. As long as they have a power of 2, we can convert them. So it's not that there are no cosine, there are no sines, they're hidden in the cosine. And also, there aren't any obvious signs here, but that's exactly the substitution that we're going to make. So we're going to read this cosine to the 5th x as the integral of cosine to the 4th, and then the cosine x that one factor of cosine is going to be the dW, and cosine to the 4th I can convert. So specifically, I'm going to read this as cosine squared x squared. And then I'll replace the cosine squared with 1 minus sine squared. Because now I'll have a polynomial in sine. That one factor of cosine is going to be my dW. And this is the sneakiest substitution that we've done. Because we have to make a substitution And W equals something that doesn't appear to be there at the beginning. The obvious substitution, W equals cosine x, W equals cosine x, well, that was a trap. How's everybody okay? I should probably finish this. So now that I make the substitution W equals sine x, this is going to be the integral of 1 minus W squared squared dW. Which we can just multiply out. If we can get powers of W, then we should get powers of W. So it's going to be 1 minus 2W squared plus W to the 4th dW. And then you can just integrate from there. How's everybody okay? So looking at this cosine of the 5th x and the substitution that we made, and the previous problem, sine to the 4th, cosine to the 3rd, where in this problem, cosine to the 5th, we made the substitution sine, so that one factor of cosine could be the dW. And in the previous problem, we made W equal to sine, so that one factor of cosine could be the dW, and we had an even number left over that we can convert to sine. So what is it in products of powers of sines and cosines? How are we going to make the decision as to what our substitution is going to be? Don't answer me now. I want you to think about it. What is it that makes this substitution work? Then try those things. And then more importantly, when we have products of powers of sines and cosines, when is substitution not going to work? Any questions? Rad. All right, that's going to be it for today. Tell me when sine to the mx times cosine to the nx is not a substitution problem. That's it for today. I'll see y'all on tomorrow. Everybody have a good day and thanks for playing.